Well, back to some random variables. We've been looking at, I guess, 4 different distributions for doing different things. Sometimes we've been counting the number of hits, and sometimes we've been looking at the waiting time to the first hit. And there have been a couple of situations. Originally, we were looking at Bernoulli trials, where for counting the number of hits, we used the binomial distribution. Waiting time was given by the geometric distribution. So we need to know both, how to use these different distributions, but also when, what situations they apply to. And more recently, we've been looking at a Poisson process with some average rate of hits lambda. And for counting the number of hits, we use the Poisson distribution, which we got from the binomial distribution by looking at faster and faster trials. And for the waiting time to that first hit, we have the exponential distribution. That we were talking about last time, where the probability that the lifetime is more than t, that is the waiting time for that first hit, thinking of that first hit as something really severe, e to the minus lambda t. And in general, if random variable L has the exponential distribution, with parameter lambda, particularly when the hit is fatal, this parameter lambda is often referred to as the hazard rate. The rate at which those hits occur per unit time. Then we know the density function. F. I'll use t instead of x because in so many of the applications it represents time, but not all the applications. Is lambda times e to the minus lambda t, starting at time 0. And for this density function, last time we worked out the expected value, the mean lifetime, and we got 1 over lambda. Well, so for example, if say the rate of hits is 0.5 per year, then the mean lifetime would be 2 years. And conversely, if we know the mean lifetime, then we can find what the hazard rate is. And the mean lifetime is perhaps easier to measure. I mean, you just take 1,000 of those mosquitoes and average up the lifetimes, whereas directly measuring the hazard rate might be harder. But we're not done. We want the standard deviation. For a random variable L having the exponential distribution. So this is its density function. So towards that end, let's start by calculating the expected value of L squared, because then we know we can get the variance from that and so forth and so on. So in general, we know how to calculate the expected value of the square of a random variable. So in this case, t squared lambda e to the minus lambda t applies starting at 0. Well, for the mean, we gave this a big treatment in 3 separate steps. To speed things up today, let's compress the 3 steps into 1. We look at this integral and realize we'll have to do integration by parts. There's nothing else that works for this. So we'll integrate that part of it, the lambda e to the minus lambda t. It's easy to integrate. And then if we do integration by parts twice, we can differentiate away the t squared. So we do that. So we're applying integration by parts. Okay, so if we start by taking the antiderivative for this second factor, we get minus e to the minus lambda t for the antiderivative, minus, now we get to differentiate the t squared. So we got 2t, and then we put in that same antiderivative we just found, namely minus, so this becomes a plus, e to the minus lambda t. And this has to be evaluated between 0 and infinity. Well, at t equals 0, of course, it's 0. That's the easy thing. And then we plug in t equals infinity and see what we get. Well, strictly speaking, we don't plug in t equals infinity. We take the limit. As t goes to infinity, of t squared times e to the minus lambda t. Well, let me write that as 1 over e to the lambda t instead of e to the minus lambda t. And we want to plug in infinity. That is, we wanted to see what the limit is as t goes off to infinity. Well, it's an infinity over infinity limit. We do it the same time as last time. We apply L'Hopital's rule. In fact, we apply it twice to differentiate away the t squared. We apply it first. It has the same limit as 2t over lambda e to the lambda t, and then we do it again and see that the limit is 0. In other words, we plug in infinity and we get 0. We still have to do this second integral. But we did that last time. T times e to the minus lambda t. This second thing is what? 2 over lambda squared because we worked it out last time, and we did it using integration by parts. Integrating the e to the minus lambda t and differentiating away the t. Well, it speeds things up a lot. 2 over lambda squared. So the variance. Well, the variance is the expected value of L squared minus the mean squared. And the expected value of L squared, we got 2 over lambda squared. And the mean, we said, was 1 over lambda. So we square that. Two over lambda squared minus 1 over lambda squared. Finally, the standard deviation is 1 over lambda. Well, we've seen 1 over lambda before recently. It was the mean. So the mean and the standard deviation turned out to be the same for the exponential distribution. So let's work the usual problem. What's the probability that we get a measurement within 1 standard deviation of the mean? So for the exponential distribution. Last time we did it, it was for the uniform distribution. Okay, where the hazard rate is lambda. So the answer might depend on what lambda is. We'll see. We want the probability that L differs from its mean by no more than 1 standard deviation. Well, so to rewrite that, the event distance from L to mu is no more than sigma means that L is not too small and not too big. It's at least one standard deviation below the mean, and it's at most 1 standard deviation above the mean. So we know what the mean and the standard deviation are for L. 1 over lambda minus 1 over lambda. Mu minus sigma is just 0. And mu plus sigma is 1 over lambda plus 1 over lambda. So the problem turns out to be nothing but finding the probability that we get a measurement in this interval. So we'll just integrate the density function over this interval. Interval from 0 to 2 over lambda, density function. Well, so we take antiderivatives again. Same one as usual. We plug in t equals 2 over lambda. So we have minus e to the minus lambda times 2 over lambda. Well, so the lambdas cancel. Minus, and now we plug in t equals 0, and we get minus 1, so now it's a plus 1. 1 minus e to the minus 2. Well, I'll write that as 1 over e squared. Turns out there's no lambda in the answer. I mean, the probability of being within one standard deviation of the mean for the exponential distribution is independent of what lambda is. And this is about as far as we can go without a calculator, but to 3 figures, it's 86.5%. And it's independent of what lambda is. Well, let's work the following problem. Suppose we have some organism whose lifetime we think is exponentially distributed. Well, so that means that old age is not a problem. There are other problems that kill this thing off. Assume that the lifetime of an insect, some particular species of insect, is exponentially distributed. Okay, so with a hazard rate, 1/50th per day. Okay, so that the average rate of hits is 1/50th per day, where a hit means it's the end. Well, what's the probability that a randomly chosen insect will survive the first 10 days? That should be pretty big. After all, if the hazard rate is 1/50th per day, we know what the mean lifetime is. (50 days). If the mean is 50 days, surviving the first 10 days should be not that hard. Well, given that it makes it through the first 10 days, what about the next 10? What's the probability of surviving the next 10 days, given that it's made it already through the first 10? Okay, well, let's knock out part A. We're asking the probability of survival to time 10. That's 10 days, the units we're working in. Well, in terms of the random variable lifetime, we want the probability that the lifetime is more than 10. Well, so we either, well, let's give it the full treatment. We could, probability of being more than 10 would be the integral from 10 to infinity of the density function. And of course, we know what lambda is. It's 1/50. Okay, so we take our antiderivative once again. We plug in infinity and we get 0. so to speak. We're taking the limit as t goes off to infinity there. Minus, and we plug in t equals 10. Yeah, we get e to the minus lambda t, where t happens to be 10. And we know we're given lambdas. 1/50th, so e to the minus 1/5. I don't know, let's write that as a decimal. E to the minus 1/5. And numerically, that's about 82%. Yeah, we figured the probability was pretty high. It's 82%. Now, we congratulate this bug at having made it to age 10. What about age 20? Well, first let me give it the long-winded version. We know about conditional probabilities. We want probability of survival to age 20 given survival to 10. Or we can write the probability that the lifetime is at least 20 given that the lifetime is at least 10. Conditional probability, we can view it as this fraction. The denominator is the probability of a given event, which we've just worked out. That's the 82%. And the numerator is the probability that the lifetime is both bigger than 20 and bigger than 10. Well, bigger than 20 covers both. Being, if it's bigger than 20, it's automatically bigger than 10. So we don't need to worry about that part. And we know how to do both the numerator and the denominator. We did the denominator here, and the numerator is just the same. To say some of it again, to survive to age 10, that probability is integral 10 to infinity of the density function. Probability for 20, probability the lifetime is more than 20, would be 20 to infinity. And we did this one, e to the minus 10 lambda. And this one is just the same, except 10 is 20. This simplifies, right? Using exponent laws. That exponent minus this exponent. So 20 plus 10, that's 10. What do you know? It's 82% again. Could we have seen that directly? Yeah, part B is the same as part A because a Poisson process has no memory. So we apply what we know about a Poisson process. It's independent of the past. When a hit comes, and here the hit is fatal, and it's independent of the past, has no memory. Whether we start the clock running at time 0 and let it run for 10 days, or for an organism that's alive at 10 days, we could start the clock then, and it runs another 10 days. The exponential distribution is giving the time to the first hit in a Poisson process, and there's no memory. So we could start the clock anywhere if the mosquito is alive at that point. So let me say that again, because then we want to change the rules. What if it's not a Poisson process? What if it's not the exponential distribution? Well, first things first. If the lifetime L is exponentially distributed, with hazard rate lambda, then for an organism that's alive at some time, any old time, we could think of that as time 0, time 10. It's when we'll start the clock. The probability of surviving another time period an additional time T star, to match the book's notation, T star, is the thing we've just worked out. The probability that the random variable is more than T star, lifetime e to the minus lambda T star. Well, we did it when lambda was 1 over 50, and T star was 10. But the same calculation is going to work in general. Now, let's change the rules. Suppose the hazard rate is not constant. Suppose the hazard rate changes with the age of the organism. The hazard rate is, well, we can no longer just talk about some constant lambda. We have a function of time. This is the hazard rate at time t. And sometimes might be more dangerous than others. And so the hazard rate could go up. Right? When that mosquito first gets its driver's license, the hazard rate jumps up a little, and then maybe later it'll go back down. Well, now what's going to be the probability for an organism that's alive at some time to survive some additional time T star? Good question. Let me tell you what the answer is. in this case, where we're given some function for the hazard rate, for an organism that's alive at time 0, okay, when the hazard rate is lambda of 0, but it's going to change later, perhaps. We want the probability of surviving to time t star is given by the following formula. So we want the probability of surviving to age t star. Or in other words, the probability that the lifetime is more than t star. Well, for constant lambda, we know what it looks like. Integral 0 to t star. And we integrate this hazard rate function. Okay, I don't want to use t for the variable of integration here because we've got a t tied up for another thing. Lambda of u du. Well, they say 3 things about this formula. One of them is it covers the constant hazard rate case. In particular, if this hazard rate function is just some constant, we just call it lambda. So you integrate a constant from 0 to t star, you get that constant times t star. So we have e to the minus that constant times t star. Exactly as before. So at least this isn't inconsistent with what we said about constant hazard rates. Second comment. Here's an even better formula. Suppose we don't want to start at time 0, we want to start at some other time. Say we know the organism is alive at time, some time or another. So it's alive at t0. And we want the probability of surviving to some later time t star. Okay, so we want the probability of survival to age t star, given that it has already survived to time t0. Or to write it more compactly, the probability that the lifetime is more than t star, given that it's at least bigger than t0. is given by, well, it's the same thing except we integrate from t0 to t star that hazard function. Well, so it's almost the same formula, except made a little more general. Instead of starting the clock at day 0, we could start the clock at day 10 and see what the probability of making it to day 20 is. And third comment, let me tell you where this formula comes from. Well, it comes from things we know, but applying them over and over. In particular, we know that the chances of surviving for a little bit with a constant hazard rate. But if the hazard rate keeps changing, well, we could do the following. So we want to say, oh yeah, okay, this was number 2. We have this organism that's alive at time, the early time, t0. What about that later time? Well, we'll do an approximate answer, which we'll get by partitioning that time interval from t0 up to t star into lots of little pieces. And over any one piece, the hazard rate won't change very much, we figure. It's probably some continuous function. Into n pieces on the same length, call it delta t. So we start at t0, delta t later we come up to call it t1, delta t after that we come to time 2, t2, and so forth and so on, t sub n minus 1, and t sub n is the right end point. And for this organism to survive to age t star, it's got to survive this little piece and this piece. Hey, it's got to survive all of these. And the probability of doing that surviving all n pieces is approximately. Well, it's an approximation because I'm going to pretend that the hazard rate is constant because that's what we know. So for that first little time interval, t0 to t1. Well, if the hazard rate isn't going to change a whole lot there, we'll just take its value at t1 and pretend it's constantly that hazard rate for the whole thing. And then we know e to the minus lambda, the length of time, would be the probability of making it through that first little piece. And given that it's made it through that first little piece, now it's got to get to t2. Well, hazard rate isn't going to change a whole lot during that short time interval. We'll just take lambda at t2 and pretend it's constant. Well, we're going to do the same thing for all of these. And of course, we multiply. This is the probability of making it to T2, given that it's made it to T1. We multiply to get the probability of the intersection. We do this for all of these. Last one is at Tn, that's Tn. And we multiply them all out to get the probability of surviving all n time intervals. Law of exponents says to multiply these, we add the exponents. So we get the sum, I equals 1 to n, lambda t sub I times delta t. You look at that exponent and you say, aha, that's nothing but the Riemann sum. So in the limit, we're going to get an integral. This converges to, as n goes off to infinity and we get better and better approximations, e to the minus. Okay, and that Riemann sum gives us the integral lambda u du, and we started at t0. We went up to t star. Yep, that's where this formula comes from. The book derives it in a somewhat different way, but they end up with the same formula. So let's work a problem. Before we were looking at an insect facing a hazard rate of 1/50th per day. Now let's make life a little more dangerous. The lifetime of some species of insect that we're looking at is determined by the following hazard rate. Lambda at time t is 1 plus t over 50. Okay, so at time 0, it's 1/50th. And this is units of per day. So it starts at 1/50th, but as time goes on, yeah, I mean, after 49 days, right, lambda is 1. I mean, that's pretty dangerous. It starts at 1/50th, but then increases. We could ask the same two questions. We'll probably have time to do the first one. What's the probability insect survives the first 10 days? That is, at the time 10 days. So it's alive when we start the experiment. We want the probability that it reaches age 10 in days. Okay, let me emphasize that this is with a variable hazard rate, L is not exponentially distributed. The exponential distribution, we had a constant hazard rate. And we have various formulas that apply to the exponential distribution, but they won't apply here. But we can apply this modified version of it. We want the probability of survival survival to 10 days. In other words, the probability that L is more than 10. Well, we're starting at day 0 and going up to 10. E to the minus integral 0 to 10 of the hazard rate. So when we had a constant hazard rate, well, we just had 10 times 1/50th, but now the hazard rate is changing.
Could you explain again why it's not an exponential distribution?
It's because the hazard rate is not constant. Yeah, the exponential distribution gives us time to first hit in a Poisson process where the rate of hits is independent of the past and doesn't depend on what time it is. If it were exponentially distributed, the answer would be e to the minus 10 lambda, and we'd stop. Well, let's work this out. I mean, that integral, 1 plus 2. Well, we're just integrating a constant function. Let's take the 1/50th out in front. So we're integrating 1 plus u. We pick some convenient antiderivative, like u plus u squared over 2. We plug in 10 plus 100 over 2. And then we plug in 0 and we get 0 and we subtract. 10 plus 50. Yeah, 6 over 5. This integral is 1.2, so the probability is e to the minus 1.2. Well, then we ask our calculator what that is. It's around 30%. Well, I mean, before we got 80-something% to survive the first 10 days, where the constant rate was constantly 1/50th. But now with this varying constant rate, yeah, life becomes a lot more hazardous by the end of 10 days. It's up to 11/50th. It's a lot bigger. So there's a smaller probability of living to the ripe old age of 10 days. Well, got to stop here for this week.